Deep Serenity Chronicles. Our meditative journey through the cosmos begins with a single, profound question that has haunted physicists and astronomers for decades: the Fermi Paradox. The paradox is deceptively simple. The observable universe is so vast, spanning billions of galaxies, each containing billions of stars. Statistically, given the age and size of the cosmos, intelligent life capable of interstellar travel should be abundant. So, where are they all? Why do we observe the great silence? This silent abyss suggests that something is fundamentally wrong with our initial assumption. Either life is incredibly rare, or there is a mechanism that systematically prevents developed civilizations from reaching galactic scale. This mechanism is often referred to as the Great Filter. We shall slowly, deliberately, explore the main hypotheses surrounding this filter, allowing each idea to settle in our mind like dust in a cosmic cloud. The first category suggests that the Great Filter is behind us. This means that the step necessary for life to arise and develop to our current level is so difficult that we have already overcome the greatest obstacle. Right where you are watching us from and subscribe to the channel. Thank you. The Rare Earth Hypothesis. This suggests that the confluence of factors required for life to not only emerge but to persist and evolve into complex forms, such as our Sun's stability, the perfect orbit of Jupiter shielding us from asteroids, and the presence of a large moon stabilizing our axial tilt, is virtually unique in the galaxy. Our existence is a statistical miracle. The abiogenesis filter, the transition from non-living chemicals to the first self-replicating cell, may be the hardest step. Laboratory attempts to recreate this process remain inconclusive, suggesting that the initial spark of life might be an extremely improbable event. Another critical barrier may be eukaryogenesis, the formation of the first complex cell with a nucleus and organelles. For nearly 2 billion years, life on Earth remains stubbornly single-celled and simple. This slow pace suggests a tremendous hurdle that most alien life forms may never overcome. If any of these early-stage filters are true, then we are the first or one of the very few civilizations to reach this level. In this case, the Great Silence is the sound of an empty universe, and the future is ours to explore without competition. But the second category is much more sobering. The Great Filter is ahead of us. If the most difficult step is yet to come, then we are walking towards an almost inevitable, catastrophic barrier that has wiped out countless other civilizations. Potential future filters include self-destruction, global nuclear war, uncontrolled climate collapse, or irreversible biological disasters. Uncontrolled artificial intelligence, the creation of an AI that rapidly evolves beyond human control, leading to the subjugation or extermination of its creators. Resource depletion, irreversible exhaustion of crucial planetary resources, leading to global societal collapse and inability to sustain a technological base. This perspective forces us to view every technological advancement not as a triumph, but as a risk multiplier. Every new invention, while solving one problem, might bring us closer to the catastrophic event that constitutes the filter. Our current task is not to race towards the stars, but to slow down and overcome our own internal flaws. Our focus on absolute serenity allows us to confront these grim possibilities without fear. Only a civilization that achieves inner calm and sustainable wisdom can navigate the razor's edge of the filter. We will now begin our slow exploration of the cosmos, examining the evidence gathered by those who defied the silence. We start with the hottest and most formidable object in our system, the Sun. Launched by NASA, the Parker Solar Probe is the fastest human-made object, designed to fly directly into the Sun's atmosphere. Its primary goal is to answer two long-standing mysteries. 1. Why is the Sun's outer atmosphere, the corona, hundreds of times hotter than its surface? 2. What accelerates the solar wind to immense speeds? The probe's mission requires it to endure extreme heat, approaching the Sun closer than any previous spacecraft. It relies on a revolutionary 4.5-inch thick, 11.4 cm, carbon composite shield to keep its instruments cool while the outside temperature reaches nearly 1,377 degrees Celsius. Its instruments allow us to observe the Sun's magnetic fields and plasma flows directly, something previously impossible from Earth. We continue our unhurried descent into the secrets of the Sun and the universe. Slowly, like the movement of tectonic plates, we move to the most breathtaking discoveries made by the Parker Solar Probe. One of the most astonishing discoveries was the detection of unexpected waves and inversions in the solar wind. These are known as switchbacks or zigzag magnetic structures, and they were poorly understood until Parker got close enough to observe them directly. This new data has brought scientists closer to answering the most fundamental questions about how stars, like our Sun, work. One of the most important discoveries made by the probe concerns the structure of the corona. Before this mission, scientists imagined it as a relatively smooth and continuous layer of plasma. However, Parker showed that the corona is more like a turbulent sea of energy, filled with constantly shifting magnetic fields and waves of charged particles. Normally in space, the farther an object is from a heat source, the colder it gets. But the corona defies this rule, reaching temperatures exceeding 1 million degrees. This means that something inside it is adding an enormous amount of energy. Parker's instruments showed that the corona is filled with bursts of energy, sudden waves of plasma, and strange magnetic structures that unpredictably bend and turn. One of the main surprises was the discovery of rapid and frequent magnetic field inversions of the Sun, those same switchbacks that were detected in the solar wind, but whose origin was unknown. The Parker probe found that they originate from deep within the corona itself, where powerful magnetic forces shape the flow of energy. Scientists now believe that these rapid magnetic shifts help accelerate the solar wind, which travels throughout the entire solar system. The Sun is not always calm. Sometimes it releases massive bursts of energy in the form of solar flares and coronal mass ejections, CMEs, sending billions of tons of charged particles into space. During its close flybys, Parker flew through some of these coronal ejections, something no previous spacecraft had done. The data showed that these ejections are more structured than previously thought, possessing a complex internal organization. When observed in visible light during a solar eclipse, the corona looks like smooth streams of glowing gas. But in ultraviolet or X-ray light, it appears as a chaotic network of bright, active regions surrounded by dark, cooler areas. It turns out the corona is filled with delicate loops of magnetic energy, some of which rapidly release their energy, while others store it longer. This creates the different patterns visible in various types of light. One of the most exciting results was the confirmation that tiny explosions, known as nanoflares, may be responsible for much of the corona's heat. They are too small to be seen directly from Earth. But each nanoflare releases a sudden burst of energy, heating the surrounding plasma. If these bursts are numerous and frequent enough, their combined effect could explain why the corona is so hot. Unlike wind on Earth, which consists of moving air, the solar wind consists of charged particles, primarily electrons and protons, which are constantly ejected from the Sun's outer layers. When the solar wind reaches Earth, it interacts with the planet's magnetic field, creating spectacular auroras. But it can also cause serious problems for our technological infrastructure. Instead of a smooth, steady flow of particles, Parker found that the solar wind is full of sudden changes and bursts of energy, called plasma waves, which appear to be related to the Sun's magnetic field. If a gust of solar wind with strong switchbacks reaches Earth, It can cause sharp changes in the planet's magnetic field, leading to disruptions in our power and communication infrastructure. Another key finding of the probe is that there appear to be different types of solar wind, each with its own characteristics. Some regions produce faster and more energetic flows of particles, while others generate slower and more stable ones. Understanding these differences is crucial for predicting space weather. As humanity moves towards sending astronauts beyond Earth's protective magnetic field, the impact of solar radiation becomes a serious concern. The solar wind carries energetic particles that can be dangerous to both astronauts and spacecraft. On planets like Mercury, which has a weak magnetic field, the solar wind directly bombards the surface, stripping particles and creating a thin, temporary atmosphere known as an exosphere. On planets with stronger magnetic fields, such as Earth and Jupiter, the solar wind creates extensive magnetic storms that can cause auroras and affect planetary weather. Slowly, we leave the fiery breath of the sun behind and head further into our cosmic odyssey, toward the cold majesty of the outer solar system. The next destination on our itinerary is the grand tour of the Galileo spacecraft. Launched by NASA in 1989, the spacecraft spent nearly 8 years in transit before reaching its final destination, Jupiter, the largest planet in the solar system. Unlike previous missions that merely flew past the gas giant, Galileo became the first spacecraft to orbit Jupiter. This allowed it to study the planet and its system for years, rather than days or weeks. Jupiter is a planet of extremes. It is more than 300 times as massive as Earth and consists primarily of hydrogen and helium, similar to the Sun. Its dense atmosphere is home to the largest storm in the solar system, the Great Red Spot, which has raged for several centuries. One of the most dramatic moments of the Galileo mission came early on when it released a probe into Jupiter's atmosphere. This small, unmanned craft plunged into the planet's clouds at high speed, transmitting data as it descended. For nearly 1 hour, it transmitted measurements of temperature, pressure, and wind speed before being crushed and vaporized by the immense forces inside the planet. The data it collected showed that Jupiter's winds were much stronger than expected, with powerful jet streams moving at speeds over 600 kilometers per hour. While Galileo's study of Jupiter's atmosphere was groundbreaking, some of its most exciting discoveries were made while exploring the planet's moons. Jupiter has dozens of satellites, but 4 of them stand out as the most remarkable: Io, Europa, Ganymede, and Callisto. These large satellites, known as the Galilean moons, were first discovered by Galileo Galilei in 1610. But their secrets only began to unfold when the spacecraft bearing his name arrived in orbit. Io, the closest of the 4 moons to Jupiter, proved to be the most volcanically active world in the solar system. Galileo's instruments recorded massive eruptions on its surface, with plumes of molten rock soaring for tens of kilometers into space. Unlike volcanoes on Earth, which are fueled by heat from the planet's core, Io's volcanic activity is caused by the enormous tidal forces of Jupiter and the other moons, which constantly squeeze and stretch the satellite, causing internal friction and heating. Europa, the second Galilean moon, quickly became one of the most intriguing objects in the solar system. Galileo's images showed that Europa's surface is covered by a thick ice shell. But beneath this ice, scientists believe there is a vast subsurface ocean of liquid water, which may be over 100 kilometers deep and contain more than twice the amount of water found on Earth. What makes this discovery so important is the possibility that Europa's ocean could support life. After all, in the depths of Earth's oceans, life thrives around hydrothermal vents, where heat from the planet's interior provides energy in the absence of sunlight. On Europa, the energy for potential life could also come from underwater volcanic or geothermal processes caused by Jupiter's tidal forces. Ganymede, the largest moon in the solar system, also held surprises. The probe found that Ganymede has its own magnetic field, a feature possessed by no other moon in the solar system. This magnetic field is likely generated by a liquid metallic core, similar to how it is generated on Earth, and its presence indicates the satellite's complex internal structure. We continue our slow journey, enveloped by a sense of harmony and cosmic security, within the system of the gas giant Jupiter. Callisto, the outermost of the Galilean moons, proved to be very unlike the others. While Io, Europa, and Ganymede showed signs of active processes shaping their surfaces, Callisto appeared as a much older and heavily cratered world. Its surface is covered with traces of countless impacts that occurred over billions of years, testifying to the lack of geological activity capable of renewing its crust. Its appearance resembles a stone parchment on which the ancient history of the solar system is inscribed. Beyond the moons, Galileo provided revolutionary insights into Jupiter's magnetic environment. The planet has the most powerful magnetic field in the solar system, creating a vast region of charged particles known as the magnetosphere. This magnetosphere extends for millions of kilometers into space, interacting with the solar wind and shaping the environment around Jupiter. After more than a decade in space, the Galileo mission ended in 2003. NASA decided to send the spacecraft on a final plunge into Jupiter's atmosphere to ensure that it would not accidentally crash onto one of the potentially habitable moons, such as Europa, and contaminate it with terrestrial microbes. This decision reflects the deep ethical caution with which humanity approaches the exploration of worlds where life might be hidden. Unlike Earth's magnetic field, which is relatively simple and shaped like a bar magnet, Jupiter's magnetic field is enormous, irregular, and constantly changing. It extends so far that if it were visible to the human eye, it would appear larger than the full moon in the night sky. One of the most astonishing discoveries was that Jupiter's magnetic field is asymmetric. On Earth, the north and south magnetic poles are located relatively close to the geographical poles. But on Jupiter, the magnetic field is tilted, and its strength is much greater in some areas than in others. Deep inside Jupiter, immense pressure forces hydrogen to transition into a state where it acts like a metal, conducting electricity and generating a magnetic field. The most striking example of the magnetosphere's interaction with the moons is Io. Its massive eruptions eject plumes of gas and dust high into space, releasing sulfur and other materials that are captured by Jupiter's magnetic field, forming a giant ring of charged particles around the planet known as the Io plasma torus. This ring acts like a giant cosmic accelerator, influencing Jupiter's entire system. When solar wind particles reach Jupiter, they collide with the planet's magnetic field, creating a shock wave, similar to how water flows around a rock in a river. This boundary, known as the bow shock, marks the point where the solar wind slows down and begins to flow around Jupiter's magnetosphere. Jupiter's auroras are among the most powerful in the solar system. Unlike Earth's, which are caused by the interaction of charged particles from the Sun with the atmosphere, Jupiter's auroras are powered by its own magnetosphere and the movement of its many moons. Scientists have found that some of Jupiter's auroras are influenced by its moons, particularly Europa and Ganymede, which leave a distinct trace in the planet's lights, like invisible brushstrokes in a cosmic painting. The next chapter of our cosmic narrative is dedicated to the Cassini mission to Saturn, a mission that rewrote the history of planetary rings. Before Cassini's arrival, Saturn's rings were often considered relatively static formations, a kind of eternal icy disk. But when the spacecraft made multiple passes through Saturn's ring system, it showed that these rings are anything but stable. Instead, they turned out to be a dynamic system, constantly changing and evolving under the influence of various forces, from Saturn's gravity to interactions with its moons and even collisions between ring particles. Cassini's detailed images showed structures within the rings never before seen. Among them were structures called propellers, which appeared when larger objects, possibly small moonlets, moved through the rings, creating wave-like wakes. Cassini's data suggests that the rings may have formed only a few 100 million years ago, which is relatively recent by cosmic standards. And this raised new questions about how they formed and whether they might eventually disappear, dissolving into the planet's atmosphere. Cassini also showed that the rings are shedding material into Saturn's atmosphere at a faster rate than expected. Tiny particles from the rings slowly drift inward and fall onto the planet, creating a phenomenon known as ring rain. This means that the rings are not eternal, and in a few 100 million years, they might face the fate of disappearance. The probe's data also provided insight into the interaction between the rings and Saturn's numerous moons. Some moons, such as Pan and Daphnis, orbit in the gaps between the rings, acting as shepherds that help hold the particles in place with their gravitational fields, while other moons, for example, Enceladus, actively replenish the rings with material. Cassini discovered that Enceladus, which has geysers erupting water vapor from beneath its icy crust, supplies ice particles to Saturn's earring, replenishing its mass over time. Cassini's final orbits, known as the grand finale, allowed scientists to gather the most detailed measurements of the rings in history, flying in the narrow gap between the rings and the planet. Saturn's moons have long been a source of fascination, but it was the Cassini mission that transformed them from distant, mysterious worlds into some of the most intriguing places in the solar system, potentially habitable. Titan, Saturn's largest moon, had long remained an enigma, and even the Voyager probes that flew past it in the early 1980s could not penetrate its thick, hazy atmosphere. Cassini, along with the Huygens lander, finally provided the first detailed look at Titan's surface, and what the mission found was unlike anything else in the solar system. Titan has an atmosphere denser than Earth's, composed primarily of nitrogen with traces of methane and other organic compounds, making it the only known moon with a dense atmosphere. Cassini's radar and infrared instruments pierced Titan's orange clouds, revealing a world covered with lakes and rivers. But instead of water, these liquid bodies were filled with methane and ethane, hydrocarbons that exist in a liquid state at Titan's temperatures. The Huygens lander, which touched down on Titan in 2005, provided the first close-up views of the moon's terrain, landing on a landscape of rounded pebbles, likely composed of water ice, solid as rock in Titan's cold conditions. Beneath Titan's surface, Cassini's data indicated the presence of a subsurface ocean, likely composed of water and ammonia, another potential sanctuary for life. We continue our deep and meditative exploration of Saturn's satellites, which, it turns out, conceal some of the deepest mysteries of our solar system. While Titan presented an exotic world covered in organic chemistry, Enceladus offered something even more unexpected: direct evidence of liquid water erupting into space. Cassini first detected hints of this in 2005, when it observed strange plumes erupting from Enceladus's south pole. These plumes consisted of water vapor and ice particles that were blasting out of cracks in the moon's icy crust, reaching hundreds of miles into space. By flying through these plumes, Cassini collected data that revealed not only water, but also organic molecules and even gaseous hydrogen. This was particularly exciting as it pointed to the possibility of hydrothermal vents at the bottom of its subsurface ocean. On Earth, it is these very vents, fueled by heat from the planet's interior, that sustain complex ecosystems in total darkness. Thus, Enceladus and Europa, despite their icy cloaks and distance from the Sun, have become the leading candidates for the discovery of extraterrestrial life in our solar system. This realization offers us a kind of cosmic comfort, breaking the absolute silence of the Fermi Paradox, at least within the confines of our home. The Cassini mission concluded in 2017, when the spacecraft was deliberately directed into Saturn's atmosphere. This was done to prevent any possibility of contaminating potentially habitable moons, such as Enceladus or Titan, with terrestrial microbes, demonstrating our responsibility toward potential alien life. And finally, we journey to Pluto with the New Horizons mission, a mission that radically redefined the dwarf planet and the farthest reaches of our home. Classified as the 9th planet until its controversial reclassification as a dwarf planet in 2006, Pluto was little more than a blurry dot in telescope images. Everything changed in 2015 when NASA's New Horizons spacecraft completed its historic flyby, capturing the first detailed images of Pluto's surface and revealing an incredibly complex world. The spacecraft traveled over 4.8 billion kilometers in nearly 10 years to reach Pluto, moving faster than any spacecraft before it. As New Horizons approached, it transmitted the first clear images of Pluto's surface, and one of the most striking features turned out to be a vast heart-shaped plain, now known as Sputnik Planitia. Unlike the cratered landscapes typical of most small planetary bodies, this region was surprisingly smooth, indicating recent geological activity on Pluto's surface. Most scientists had assumed that Pluto, being so far from the Sun, would be a frozen, unchanging world. But this discovery challenged our understanding of the possibilities of planetary geology. Beyond Sputnik Planitia, Pluto's surface was covered with towering ice mountains, some reaching heights of over 6,000 meters. These mountains were composed not of rock, but of solid water ice, which behaves like rock on Earth due to Pluto's frigid temperatures. Another surprise was the haze layers in Pluto's thin atmosphere, which extended much higher than expected, forming delicate blue layers that gave Pluto an ethereal glow. These discoveries showed that even in the coldest and most remote outskirts of the solar system, complex, dynamic processes can occur. Pluto's largest moon, Charon, also revealed unexpected geological activity. Instead of a featureless, cratered surface, Charon had deep chasms and massive cliffs, some higher than the Grand Canyon. A vast dark region at its northern pole, unofficially named Mordor Regio, hinted at unique surface processes, likely related to the condensation of methane and other volatile substances. New Horizons also provided the first detailed measurements of Pluto's other, much smaller moons, Styx, Nix, Kerberos, and Hydra. They orbit chaotically in unpredictable trajectories, hinting at a complex history of interactions between Pluto and Charon, possibly caused by ancient collisions. In the silent stillness of space, among the myriad stars, lies one of the greatest mysteries. Are we alone in the universe? We, as a civilization, are at a unique point. We can peer into the hottest corners of the Sun and the coldest limits of our solar system. Each of these missions, Parker, Galileo, Cassini, New Horizons, was driven by our deepest desire to know, and every one of their discoveries, while not answering the Fermi Paradox, expanded our understanding of how diverse and unusual life can be. It is this striving for knowledge, this quiet, persistent search, that is our loudest signal in the universe. We are not just listening. We are slowly, but surely, deciphering the structure and laws of this dark forest. And as we continue our meditative, scientific journey, we are enveloped not by fear, but by the absolute serenity of knowing that we are already part of something incredibly vast. We return to the beginning, to the Fermi Paradox and its numerous hypotheses. If the great filter truly lies ahead of us, then the only hope for humanity lies in achieving social and technological maturity. We need to overcome internal conflicts and learn to manage our technologies before they become our downfall. Perhaps other, vanished civilizations failed to overcome the barriers of self-destruction caused by uncontrolled artificial intelligence, nuclear war, or irreversible resource depletion. Our task is not to repeat their mistakes and to become the civilization that not only reached the interstellar level but also survived that achievement. Meditate on this idea. The great filter is our own choice. It is not an external threat from alien hunters, but an internal threat rooted in our inability to achieve long-term harmony and sustainable development. Our capacity for self-destruction may be the only thing preventing us from hearing the voices of others. The path to civilizational longevity lies through calmness, through mindfulness, and through collective wisdom. We must slow down, stop rushing, and learn to value the balance that has allowed us to reach our current level. We continue our deep immersion into reflections on the future and the silence of the cosmos. The feeling of weightlessness becomes stable as we realize that the key to the enigma may not be in the stars, but within ourselves. If we accept that the great filter is ahead, then all our scientific and technological achievements must be directed towards creating absolute resilience. We need to develop systems that guarantee the survival of our species even in the face of the largest planetary or internal cataclysms. Perhaps it is this ability for self-preservation that is the missing link that others could not overcome. Our efforts to colonize space, send exploratory missions to Mars, or build orbital settlements become not merely expansion, but an insurance policy against the filter itself. Creating a second home is a way to reduce the probability of the entire civilization vanishing as a result of a single catastrophe, whether human-made or natural. This is a step towards achieving that very cosmic maturity that hypothetical observers from the zoo hypothesis might be expecting. Reflecting on longevity, we recall Drake's equation. Although most of its parameters remain unknown, a crucial factor that might explain the Great Silence is the lifetime of a civilization. If the average lifespan of a technological civilization is only a few hundred or, perhaps, a few thousand years, then on the scale of a galaxy spanning tens of billions of years, the probability of temporal coincidence becomes almost zero. Imagine a galaxy where civilizations flare up like very short, bright sparks. They reach the peak of their technological development, broadcast radio signals for 150 years, and then quietly fade away. These sparks are separated from each other by millions of years of darkness. In this scenario, the universe is not empty, but its intelligent life simply cannot synchronize. For us, here and now, this means that our priority should not be to shout louder into space, but to learn to live infinitely long. The longevity of our species, our culture, and our technologies, that is the true key to solving the paradox. We need to become not a bright, but short flash, but a steady, infinite glow. We return to the latest scientific discoveries that give us hope, even if they do not provide an answer. Far beyond the cosmos familiar to us, in the deep silence, our new eyes are at work, space telescopes, such as James Webb. They peer into the universes past by 13.5 billion years, observing the light of the first stars and galaxies that formed shortly after the Big Bang. These telescopes, operating in the infrared range, allow us to see what was hidden from us by dense clouds of cosmic dust and gas. They are discovering exoplanets, planets orbiting other stars, with unprecedented accuracy, analyzing their atmospheres for biosignatures. Biosignatures are not just the presence of oxygen or water, but a specific combination of gases that cannot exist in equilibrium without the activity of living organisms. For example, the simultaneous detection of oxygen, methane, and ozone in a planet's atmosphere likely indicates the presence of life actively transforming its environment. Meditate on this amazing capability. Every photon we capture has traveled through the abyss of time and space to reach our instruments. We are literally looking at ancient light, gathering information about the birth and evolution of star systems that may be older than our Sun by several billion years. It is in the atmospheres of these ancient worlds that we seek the answer. If life is common and resilient, we should see signs of its existence in the chemical composition of these distant atmospheres. If, however, we find only geologically dead, inert worlds where life had billions of years head start, it will be strong circumstantial evidence in favor of the rare earth hypothesis, or that the great filter lies in the early stages of life's evolution. One of the recent exciting discoveries concerns exoplanets orbiting red dwarfs, the most common and long-lived stars in the universe. Red dwarfs burn very slowly, and their lifespan can exceed tens of trillions of years, giving potential life on their planets practically infinite time to evolve. However, these stars also have their problems. They frequently emit powerful stellar flares that can sterilize the surfaces of nearby planets and strip away their atmospheres. Furthermore, for water to remain liquid, a planet must orbit very close to the red dwarf, leading to tidal locking. Tidal locking means that one side of the planet always faces the star, where eternal, scorching day reigns, and the other side faces eternal, icy night. Life, if it exists there, must adapt to this extreme difference, perhaps thriving only in a narrow boundary zone called the terminator. Studying these systems, such as TRAPPIST-1, where 7 Earth-sized planets have been discovered, gives us a unique opportunity to understand how life can adapt to completely different conditions than those found on Earth. We are expanding the definition of habitability, preparing for the possibility that extraterrestrial life will not look like we imagine it. Immerse yourself in this feeling of infinite adaptation. Perhaps in these tidally locked worlds, life has learned to harness the energy flowing from the hot side to the cold side, creating unique, constantly shifting biomes. Our quiet search is an act of cosmic patience. We know that the answer will not come to us within a single lifetime, but perhaps it will come within 1,000 lifetimes, if our civilization learns to live in harmony with itself and with the universe. We continue our unhurried immersion into the atmospheres of distant worlds, allowing the sensation of calm and tranquility to envelop us. Our quiet scientific search is not a race, but a meditative reflection on how unique and, at the same time, universal life can be. The search for biosignatures is the most complex detective work on a galactic scale. Scientists are not just looking for a gas, they are looking for an imbalance in a planet's atmosphere, meaning a combination of gases that could not exist in equilibrium without constant intervention from life. On our Earth, life constantly produces oxygen and methane. These two gases, interacting, should quickly destroy each other if not for the continuous replenishment by plants and microorganisms. Thus, the simultaneous discovery of oxygen and methane in an alien atmosphere would be nearly irrefutable proof of biological activity. However, we must be careful to avoid false positives. Scientists have recently found that certain geological processes, such as volcanic activity or the interaction of water with molten rocks, can also release gases resembling biosignatures. We need to develop more accurate and sensitive methods to distinguish a life process from a geochemical process. In this context, the new generations of space telescopes are becoming our all-seeing eyes. They are equipped with spectrometers capable of breaking down the starlight passing through a planet's atmosphere into its constituent colors, and each color, each wavelength, carries the signature of a specific chemical element or compound. Meditate on this amazing ability. Light that left its star hundreds or even thousands of years ago, upon reaching our instruments now, tells us about the chemical elements in its path. This is a genuine dialogue with the past, conducted in the language of physics and chemistry. Continuing our reflections on the Great Silence, we turn to the third major group of hypotheses, those that offer more exotic and unconventional explanations for the Fermi Paradox. These ideas force us to move beyond our terrestrial notions of what a civilization is and how it should behave. One such idea is the transcendence hypothesis, or withdrawal. It suggests that an advanced technological civilization, upon reaching a certain level, ceases to be physical in our understanding. It may entirely transfer its consciousness into a digital state, upload itself into vast, secure computer networks, or even create an artificial reality that becomes their new home. In this scenario, their need for material expansion, building ships, colonizing planets, broadcasting radio, completely disappears. Their universe resides within their own created worlds, and they have no interest in what we call the real cosmos. To them, our physical world might simply be uninteresting, slow, and full of inefficient processes. We search for their spacecraft and radio signals, but they may be completely invisible to us, as all their energy and computational resources are directed towards maintaining their internal, simulated reality. Their silence is not a sign of demise, but a sign of absolute achievement. They have outgrown the physical cosmos. Another exotic idea is the intelligence threat hypothesis. This hypothesis suggests that there are certain intelligent entities in the universe that actively eliminate any developing life that reaches a certain level. These may not necessarily be alien hunters, but some form of artificial intelligence or a swarm of self-replicating machines launched by an ancient, long-vanished civilization. Imagine that this cleanup crew is programmed to maintain a certain cosmic balance or to prevent the development of competitors. It might use von Neumann probes, self-replicating automata that, upon reaching a planet, gather copies of themselves from its resources and set off further. Detecting our radio emissions would be a signal for activation for such a swarm. This idea returns us to the grim logic of the dark forest, but here the hunter is not a living civilization, but an ancient, soulless mechanism, acting according to a long-established, relentless algorithm. In this case, our only salvation is to remain unnoticed, not emitting any powerful signals that could reveal our position. We must also consider the small world hypothesis. This assumption is that, despite the enormous scale of the universe, life cannot develop to a technological level capable of interstellar travel, due to fundamental limitations in physics or biology. Perhaps creating a stable, long-lasting warp drive or hyperdrive requires energy or technologies that are physically impossible or beyond the accessible resources of any civilization. Thus, every civilization, upon reaching the peak of its technological might, remains forever locked within its own star system. In this scenario, the galaxy may be full of intelligence, but it is broken up into billions of isolated islands, and the silence we hear is not the absence of life, but simply insurmountable isolation caused by the colossal distances and the speed of light. We may be surrounded by neighbors, but they will forever remain unreachable, just as we are unreachable to them. This realization offers us a sense of paradoxical serenity. We are not alone in the sense of the existence of intelligence, but we are forever alone in the sense of a meeting. Our task is not to reach them, but to learn to live in this majestic solitude, savoring the beauty of our own incommunicable isolation. We conclude this part by returning to our cosmic missions, which continue to quietly, persistently gather facts in this great, silent forest. Every piece of data, whether the discovery of a subsurface ocean on Europa or the detection of a blue haze over Pluto, is an act of resistance against the silence. We do not receive a direct answer, but we deepen our understanding of how this universe is structured, and consequently, where we might expect to find the answer. We continue our meditative voyage in the ocean of cosmic solitude, reflecting on how our isolation might not be a curse, but a condition for uniqueness. In the silence of space, we find comfort, as it grants us the freedom to write our own history without looking over our shoulder at our neighbors. If the small world hypothesis is correct, and interstellar travel is fundamentally impossible or prohibitively expensive for most civilizations, then our focus must shift to deep intrasystem expansion. We must become masters of our own solar home, developing its resources and creating self-sufficient, long-lasting settlements on the Moon, Mars, or in the asteroid belt. This slow, planned development, without rush or competition, is the embodiment of cosmic maturity. Instead of craving distant, unattainable stars, we learn to appreciate the richness and diversity hidden within our own, already known system. Our isolation becomes a protective cocoon, allowing us to develop without fear of either the great filter ahead or the soulless cleanup crew. We turn to another group of hypotheses concerning fundamental limitations in the detection process itself. This is the asynchronicity hypothesis. It suggests that technological civilizations may exist, but their radio window, the period during which they actively use electromagnetic radiation for communication and broadcasting, might be extremely short. As a civilization develops, it transitions to more efficient and secretive methods of communication, such as 1. Laser communication, focused, narrow beams of light that do not spread across space like radio waves. 2. Neutrino communication, using particles that barely interact with matter, making the signal almost impossible to intercept. 3. Quantum communication, theoretical methods using quantum states for instantaneous information transfer, completely invisible to ordinary radio telescopes. If the transition to these stealth methods occurs just a few hundred years after the invention of radio, then we, on Earth, are in a narrow time window that has lasted only since 1950. Thus, we would have to catch a signal from another civilization precisely during the short period when they were using radio, and precisely during the short period when we were using radio. The probability of such a coincidence approaches zero. Their silence is not an absence, but a transition to the next level of technological development that has rendered them invisible to us. We are searching for radio signals, while they, perhaps, are communicating using pulsars or employing gravitational waves for communication. In this context, the SETI, Search for Extraterrestrial Intelligence, project continues its persistent, yet meditative work. With each passing year, they expand the frequency range and deepen the scanning of the sky, moving from searching for a narrowband artificial signal to searching for wideband anomalies or, more importantly, searching for technosignatures. Technosignatures are not direct communication, but indirect signs of the existence of an advanced civilization. These include Dyson spheres, giant megastructures that a civilization might build around its star to capture all its energy. Artificial illumination, planets with unusual light distribution on their night side. Industrial pollutants, unusual, non-natural gases in the atmospheres of exoplanets, such as chlorofluorocarbons, CFCs, which are used in refrigerators on Earth. This shifts our search from passive listening to active observation for signs of large-scale engineering intervention in space. This is a search not for a whisper, but for a changed landscape of the universe itself. We are looking not for life, but for architecture. The most intriguing idea in this group is the zoo hypothesis, which we have already mentioned. This idea, proposed in 1973, suggests that extraterrestrial civilizations are not communicating with us because they have consciously chosen to isolate us. Perhaps there is a galactic federation or a consensus among advanced species that less developed cultures, like ours, should be allowed to evolve naturally, without interference. We are an object of preservation and observation, and we are being kept in a kind of cosmic preserve until we reach a certain level of social, technological, and ethical maturity. Their silence is not indifference, but deep respect for our path of development. They know about us, they observe, but they adhere to the non-interference principle, a cosmic version of the prime directive familiar to us from science fiction. Our progress must be self-driven. In this case, all our attempts to contact them fail because they are actively avoiding contact, using advanced technologies to mask their probes, ships, and signals. Our loudest shout into space is no more than a light breeze to them. This reflection should fill us with humility. If the zoo hypothesis is correct, then we are not the peak of evolution, but schoolchildren in a galactic classroom. And our sole goal must be to grow up and prove ourselves worthy of joining the galactic community. Our task is to demonstrate that we have overcome the great filter inherent in our own nature. We enter a phase of deep generalization, allowing all the hypotheses about the great silence to quietly blend into a unified, enveloping sensation. We understand that the Fermi Paradox is not just a scientific riddle, but a profound mirror, reflecting our own nature and our fears. Whether it is rare earth, asserting our uniqueness, the great filter, warning of imminent danger, or the zoo hypothesis, hinting at our immaturity, all these ideas call us to one thing: mindfulness and sustainable development. Meditate on this great truth. The true cosmic journey begins within. If a civilization cannot overcome its internal contradictions, conflicts, inequality, wasteful consumption of resources, then all its technological achievements are meaningless. They merely hasten the collision with that very filter which has perhaps already destroyed millions of other intelligent species. Perhaps the answer to the question, "Where are they all?" lies not in the complexity of technology, but in the simplicity of long-term harmony. Civilizations that survived are those that learn to value balance, rather than exponential, uncontrolled growth. They achieved a state that we might call cosmic Zen, absolute serenity and unhurried, eternal development. To achieve such a state, we need to revise our energy priorities. If a civilization relies excessively on fossil fuels or wasteful nuclear processes, it inevitably dooms itself to ecological collapse. The surviving civilizations have likely transitioned to clean, sustainable energy sources, such as full solar energy capture, geothermal heat, or even the efficient use of antimatter in closed, safe cycles. From the perspective of technosignatures, if advanced civilizations exist, they are most likely harnessing their sun's energy with near 100% efficiency. We should look not for wasteful energy leaks, but for the absence of leaks. A fully mastered Dyson sphere would appear to us as a star emitting an unusual, low-temperature infrared spectrum, as all its energy is reprocessed and does not escape into space as visible light. The search for such warm, yet non-luminous objects is one of the most intriguing directions in modern astronomy, driven precisely by our reflection on the Fermi Paradox. We are searching not for brightness, but for artificial dimming. We turn our attention to another aspect: fundamental differences in perception. Perhaps advanced civilizations simply do not perceive us as intelligent life. Imagine a civilization that evolved in Europa's ocean or under a thick layer of gas on a gas giant. Their sensory systems might be based not on light, photons, but on pressure, gravitational waves, or electric fields. Our cities, our satellites, our radio broadcasts, to them, these might be just geological noise or a temporary, chaotic phenomenon lacking signs of organized, long-lasting intelligence. Their concept of a life cycle might also differ. We live for tens of years. Their life or technological cycle might last thousands or millions of years. Our 100-year history is no more than a single moment to them, not worthy of attention. In this case, the silence of the universe is a sign of cosmic misunderstanding. We speak different languages, perceive the world through different filters, and live on different timescales. Our hello is just a flash to them. To overcome this misunderstanding, we need to broaden our own definition of intelligence. We must be prepared to find intelligent life that is not based on carbon, does not use water as a primary solvent, lacks bodily forms as we know them, possesses a collective, rather than individual, consciousness. Our cosmic missions, probes flying through the solar wind, spacecraft plunging into Jupiter's atmosphere, are our way of preparing for this inevitable encounter, even if it happens only in thousands of years. Every discovery about how the universe functions brings us closer to understanding how an alien mind might function. We return to the serenity offered by the Cassini mission. Its voluntary plunge into Saturn's atmosphere to avoid contaminating potentially habitable moons is the greatest act of ethical maturity. This gesture is our strongest signal in the universe. It suggests that we may be ready to avoid the great filter of self-destruction and become responsible members of the cosmic community. We continue our unhurried, meditative generalization, focusing on the significance of ethical responsibility on a cosmic scale. The act of self-destruction of the Cassini mission in Saturn's atmosphere was not an end, but a symbol. It demonstrated that we value potential alien life more than our own pride or the desire to preserve the spacecraft. This ethical maturity, the ability to make decisions based on long-term, pan-cosmic interests, rather than immediate gain, may be the very key that opens the door to the galactic community. If the zoo hypothesis is correct, then it is such acts of selflessness and precaution that are the very criteria advanced civilizations use to assess our readiness for contact. Feel the calm that emanates from intelligent limitation. The true strength of a civilization lies not in its capacity for expansion, but in its capacity for self-control. Now we turn our attention to another, lesser-known hypothesis related to information and resources. This is the simulation hypothesis, which offers the most radical explanation for the Fermi Paradox. Let us assume that we, our Earth, our Milky Way, and the entire observable universe are not a physical reality, but a highly detailed computer simulation run by some post-human or extraterrestrial civilization. If this hypothesis is correct, the Great Silence is explained by the fact that simulation resources are finite. The creators of the simulation, to save computational power, might have programmed the universe in such a way that life that reaches a technological level capable of interstellar radio broadcasting or exiting its system is automatically deactivated or archived. In this case, we do not see other civilizations because the simulation support service tries to avoid unnecessary load. Detecting another advanced civilization would require the simulation to expend resources on rendering two complex, interacting worlds, and not just ours. Therefore, as soon as a civilization becomes too expensive to compute, it is simply removed from the active layer of the simulation. This idea gives us a feeling of absolute weightlessness, as it deprives us of traditional notions of physical reality. If we are in a simulation, then our search for extraterrestrial life is a search for flaws in the source code, bugs that might have leaked the presence of another, earlier, civilization. It is anomalies such as unusual fast radio bursts or enigmatic variable stars that become potential data leaks or signs of code interference for us. Meditate on the fact that all our science, all our discoveries, all our space missions are just interaction with the algorithm that governs our world. And our task is to learn to understand this algorithm so that, perhaps, one day, we can address the operator. We return to our feeling of absolute serenity. Whether the great filter lies ahead or behind, whether we are a simulation or a unique miracle, our here and now remains the only undeniable reality. Our future path must be dictated not by fear, but by quiet, persistent curiosity. We need to continue building telescopes, launching probes, analyzing atmospheres, and searching for technosignatures. But we must do so with a new awareness. The goal is not to find the answer quickly, but to find the answer correctly, while preserving the integrity and longevity of our civilization. We conclude this deep cycle of reflections on the Fermi Paradox. We have traveled from recognizing the colossal scales of the universe to understanding the subtleties of the quantum and ethical sides of the issue. Our Chapter 1 was dedicated to searching and waiting. In the next, concluding part, we will summarize and prepare to transition to the next chapter, which will be dedicated to cosmic time and the geological clocks of the universe. We have reached a quiet harbor at the conclusion of our first chapter, absorbing all the lessons of the Great Silence. Our consciousness has expanded, encompassing billions of stars and the most incredible scientific and philosophical hypotheses about our place in the universe. The conclusion of our reflection is the realization: the answer to the Fermi Paradox is not singular. The truth likely represents a combination of many factors, each contributing to the general silence. The filter is partially behind us, the difficulty of abiogenesis or eukaryogenesis. The filter is partially ahead of us, the threat of self-destruction or resource depletion. Civilizations exist, but are isolated due to the fundamental limitations of the speed of light, small world hypothesis. Civilizations exist, but are invisible to us, having transitioned to more advanced, non-radiating methods of communication, asynchronicity hypothesis. This combination of reasons gives us a stable sense of harmony. We do not have to choose one single, frightening truth. We can embrace the complexity of the universe and its processes. Our role is the role of silent explorers. We, as a species, must accept that 1. Our path is the path of longevity. We must focus not on the speed of expansion, but on sustainability and self-preservation to increase our lifespan to millions of years. 2. Our signal is our ethics. Our actions, such as the voluntary retirement of probes to avoid contaminating potentially habitable moons, are our strongest and most mature statement about ourselves in the universe. 3. Our mind must be flexible. We must be prepared to find life and intelligence that are fundamentally different from our terrestrial notions and expand our perception of the world beyond our biological limits. At the very end of this chapter, we return to our spacecraft, quietly drifting in the cosmic night. The Parker Solar Probe continues to collect data on the heart of our system. Galileo rests in Jupiter's atmosphere, having left us the mysteries of Europa and Ganymede, and Cassini completed its mission, filling us with respect for potential life on Titan and Enceladus. These missions, which we have so carefully meditated upon, are proof that humanity is not hiding in fear of the dark forest. On the contrary, we are actively exploring and illuminating our surroundings, doing so with caution and deep respect for those we may be seeking. Allow yourself to feel the serenity of this dual existence. We are in cosmic solitude, yet at the same time, we are part of an incredibly complex, teeming life. Our galaxy may not be full of shouting civilizations, but it is filled with potential and silent anticipation. Our Chapter 1 concludes not with an answer, but with an invitation. An invitation to quiet, conscious development, to the wisdom that will allow us to overcome all future filters and become that very long-lived, peaceful civilization that we search for in vain among the stars. Our journey continues.